Okay, so today we're going to talk about how to find the matrix inverse and how to use it to solve a system of equations to find AX equals B. Okay, so as you may remember, the inverse of a number is basically whatever you multiply to that number to get it to equal 1. So starting simply, the inverse of 5 is 5 times 5 to the negative 1, and we get 1. That's because 5 to the negative 1 is 1 over 5. Times 5, cancel out, and we get 1. Now, with matrices, it's a little bit different. A matrix is an n by n matrix, meaning it has the same number of rows as columns, is invertible if there is a matrix that we multiply to the original to get the identity matrix. Now, this is a little bit harder to find than 5 times 5 to the negative 1 because matrix multiplication is not commutative. For example, if we have A is equal to 1, 2, and B is equal to 3, 4. AB is 1, 2 times 3, 4. So we have 3 plus 4 is 7, and 6 plus 8 is 14. But when we multiply B times A, we get 3, 4 times 1, 2, and we get 3 plus 6 is 9, and 4 plus 8 is 12, which is obviously not the same thing. So it's actually pretty simple to find the inverse of a matrix. Okay, so given a matrix, A equals A, B, C, D. In order to tell if the matrix is even invertible, we simply multiply A times D and subtract B times C. If this value is not equal to 0, then we know that the matrix is invertible. Now, in order to actually find the matrix, we simply divide 1 by this, AD minus BC, and multiply it times D negative B negative C A. Now this number right here, AD minus BC, is called the determinant of the matrix, and it's actually pretty useful in a couple of other processes. Okay, so let's just do a quick example on determining the matrix. So if we want to find the inverse of A, given that A is 3, 5, 4, 6. Now, if we want to see if this function is even possible, we simply find the determinant of A, which, as we remember, is AD minus BC, which is the same thing as 3 times 6, which is 18, minus 4 times 5, which is 20, which is equal to negative 2. Now, negative 2 is not equal to 0, so we know that the matrix is invertible. We should do this before beginning any problem. Alright, now to actually find the matrix that is in order to actually find the inverse matrix, we do 1 over the determinant, which we found to be negative 2, and we multiply that by D negative B negative C A. So we know that, alright, so we know that D is 6, negative B is negative 4, negative C is negative 5, and A is 3. So for our answer, we have the inverse matrix A is 6 divided by negative 2, which is negative 3, negative 4 over negative 2, which is 2, negative 5 over negative 2, which is 5 over 2, and 3 over negative 2. Okay, now something that we can actually use the inverse for is solving a system of equations. So using the inverse that we found just now, to be negative 3, 2, 5 over 2, and negative 3 over 2. Using this inverse, we can solve the system 3x1 plus 4x2 equal to 3, and 5x1 plus 6x2 equal to 7. Now, we know that AX is equal to B. Now, with some simple algebra, we can rearrange this into something that we can use for this problem. So we know X is B over A, which is the same thing as B times 1 over A. And 1 over A is the inverse of A. So now we find that x is equal to b times the inverse of A. Okay, so now to solve this is pretty simple. So we have x equals b times the inverse of A, and we know the inverse of A is negative 3, 2, 5 over 2, negative 3 over 2. And in this case, the matrix B is simply 3, 7. So if we go ahead and multiply everything out, we find the solution set to be 5, negative 3. All right. So we know this is pretty simple with a 2 by 2 matrix, but what if we have something like a 3 by 3, a 4 by 4, basically anything that you'll probably get on a test, it's a little more difficult. So in order to find the inverse of, let's say, the matrix A, 0, 1, 4, 1, 0, negative 3, 2, 3, 8, we actually have another method in which we simply augment A times the by the identity matrix. After row reduction, whatever we get here will be our inverse. So let's quickly run through this problem. Now we augment this with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Alright, so for sake of time with the video, I'm going to skip some of the row reductions and show that in conclusion, we want to put it in reduced echelon form, which means that we will get the identity matrix on this side, and whatever values we get here is going to be our inverse matrix. So after a ton of row reducing, we will find the inverse to be this value. Okay, so you are probably thinking, why do we need this? What do we use the inverse of a matrix for? And it's actually pretty helpful in a couple of different scenarios. So basically, if you know that A is an invertible matrix, you know a lot of other things about the matrix also. So let's say we know that A is invertible due to the simple solution by finding the determinant. If it's not equal to 0, we know it's invertible. Since we know that A is invertible, we know a lot of other things about A as well. We know that A is starting as A is an n by n matrix. If it's invertible, we know that A has n number of pivot columns. We also know that the solution AX equals 0 has only one trivial solution. We know that the columns of A form a linear independent set. We know that the columns of A span R to the n. We know that the equation AX equals B has at least one solution for each B. So basically, we know a lot of things about A. If A is invertible. So to sum it up, basically to take some key points with you in order how to find the inverse of a matrix, you want to begin find the determinant of A, which is AD minus BC. If it's not equal to 0, we know it's invertible. In order to find the inverse, we simply do 1 over the determinant of A times D, negative B, negative C, and A. If it's not a 2 by 2 matrix, we can find the inverse by augmenting A to the identity matrix. We put it in reduced echelon form, and whatever we get over here is our inverse. Okay, I hope this was helpful. Good luck with your math.